Hello everyone, welcome to this 23rd online lecture session of the course Engineering Thermodynamics. So in our previous lecture, we have first completed our discussion on the absolute thermodynamic temperature scale, and that has helped us in defining the maximum efficiency of heat engine, refrigerator and heat pump. After that, we have started our discussion on the very important topic which we call as nothing but Clausius inequality. And as per Clausius inequality, cyclic integral del Q by T has to be less than equal to 0, and we have seen this inequality is applicable for every type of process, whether it is reversible or irreversible. Okay, and moreover it has worked in both forward, means heat engine direction, as well as in the refrigeration cycle. Okay, then this particular inequality has given origination to one very important property, and that important property we call as S, which is called as nothing but the entropy of the system. Okay, so ds we have seen is nothing but equal to cyclic integral del Q by T. Okay, now so till this moment we have only used the concept of Clausius inequality for defining our new property ds, and I have told you in my previous lecture that though I am defining this del Q by T over here particularly for the reversible process, and then I am saying that it is my property, but as it is property, so that's why if we are having any kind of reversible process, if say path of the process is different, then also our value of entropy between the two state points will be same. Okay, so let me now just prove this particular point, that why entropy is a property and it is not depending upon the path. Okay, so what I will be doing, let me consider that I have my pressure volume axis. On this pressure volume axis, let us consider this is thermodynamic state number 1 and this is say thermodynamic state number 2. Okay, and one process has happened from point number 1 to point number 2, and let us consider the path taken by this process is nothing but A. Okay, then one more process has happened, but it has happened in the reverse direction from state number 2 to state number 1, and the path taken by it is nothing but B. Okay, now let me take one more process C, and this process C has happened in forward direction. Okay, so once again this path taken by it is referred to as C. Okay, now you can clearly see that I have this one combination for obtaining the reversible process as A and B. A is moving in forward direction and B is moving in reverse direction. Another combination which is completing the thermodynamic cycle in between these two states 1 and 2 is C and B. So C is moving in forward direction and B is moving in backward direction. Okay, so let me first take processes A and B. So when I'll be taking the processes A and B, I can say that cyclic integral of del Q by T will be nothing but integral from 1 point to 2 point, and this integral I have to obviously take along which path? Path A, because while we are moving from 1 point to 2 point, we are having our forward path of the process as nothing but path A. Okay, then we are moving backward from 2 to 1. So while we are moving from 2 to 1, let us consider during that time del Q by T is nothing but integral 2 to 1 del Q by T, and this is happening along path B. Now one important point I would like to highlight over here, all the processes A, B and C, we are considering over here that all the processes are nothing but reversible. Okay, so whatever the processes, different processes A, B, C, I have represented between the two thermodynamic states 1 and 2, all are actually reversible. Okay, so what we will be finding, so this is my like breakup of cyclic integral del Q by T for these individual processes if I consider path A and path B. Now obviously if I am saying that all the processes are reversible, we know from Clausius inequality that cyclic integral of del Q by T has to be equal to 0, for a reversible process. Okay, so now if process A and process B both are reversible, then obviously cyclic integral del Q by T will be nothing but equal to 0. Okay, so let me call as nothing but my equation number 1. Okay, now let me take the another equation, and for considering the once again the Clausius inequality, now I will take path C and B, which are actually completing our cycle. Okay, so now what I can do, I can define that cyclic integral of del Q by T for process C to V is nothing but equal to integral 1 to 2 del Q by T, and this integral has to be taken because now I am changing state from 1 to 2. So 1 to 2 is actually happening along path C. So I'll be writing over here path C plus cyclic integral not cyclic, plus integral from 2 to 1 del Q by T, and reverse we are doing along path B only. So B, and once again because all the processes are reversible, so this will also be equal to 0. Okay, so let me consider this is my equation number 2. Okay, if now I do 1 minus 2, so if I take 1 minus 2, so what will be happening from 1 minus 2? You can see this del Q by T 2 to 1 through path B is common in both the equations 1 and 2. So it will be cancelling out, and I'll be simply finding that integral 1 to 2 del Q by T along path A minus integral 1 to 2 del Q by T along path C is equal to 0. So that I'll be getting from 1 minus 2. So if I further simplify this, if I take one of the term on the other side, I'll be finding that integral del Q by T along path A from 1 to 2 is nothing but equal to integral 1 to 2 del Q by T along path C. Okay, so it means that if I have a reversible process, then irrespective of the path, if our thermodynamic state is changing between the same limits, in that case what will be happening, our integral del Q by T for that particular process will be same, okay, irrespective of the path of the process. Okay, so you can clearly see in this particular PV diagram, state 1 and state 2 are limited to the same point, and in one case through path A process is happening, some process is happening, and obviously it is following some path A, and then one more process is happening which can also change the thermodynamic state from state 1 to state number 2, but it is following some different path C. Okay, but one thing we can clearly see that irrespective of the path, if our processes are reversible and thermodynamic states are specified, our integral del Q by T for that particular process between the two thermodynamic states will be same irrespective of the path. Okay, so it means that in the previous lecture, mainly we defined entropy based on the concept of cycle only, but after seeing this particular illustration, we have come to know that if we have a reversible process, okay, if we have a reversible process, then irrespective of the path for reversible process, del Q by T is actually remaining fixed. So if del Q by T is remaining fixed, it means it is becoming nothing but a state function. So if it is becoming state function, I can simply say that integral del Q by T is nothing but equal to ds. Okay, so this is one very, very important point. Where obviously if I say that my integration is from limits 1 to 2, then I can simply write this ds as nothing but equal to S2 minus S1. Okay, so this is one very, very important point which we have to take care, that ds is nothing but equal to integral del Q by T for a reversible process. So this is applicable for reversible processes. For any kind of reversible process, our ds will be nothing but equal to integral del Q by T. Okay.
Excuse me, sir.
Yes.
Sir, yesterday you wrote ds is equal to closed integral of del q by t.
Yes.
Sir, today it is open.
Yeah, so that
Smooth
is what I
cycle.
am saying, that while I have defined the concept of entropy, at that time, by considering the Clausius inequality, we have used the help of cyclic integral in order to define that property. Okay, but whatever the demonstration I have shown over here in this particular slide, for a process which is operating between thermodynamic states 1 and 2, we have seen that our integral del q by t between specified thermodynamic states is actually independent of the path of the process if processes are reversible. Okay, so because of that, what is happening? Because of that, I can simply say that integral del q by t between specified thermodynamic states will be equal to ds if our process is reversible. Is this point clear?
Yes, sir.
Okay, so we have got ds equal to integral del q by t for our reversible process. Okay, so now let me define this property entropy. So we have already got entropy. Now let me show how it actually looks on property diagram, and how we can obtain. So already, though we were not knowing about the property entropy, but while we have discussed our steam tables, at that time I have already shown you that how we can calculate the value of entropy from our steam tables. But let me once again demonstrate. So what we are having, let me plot another kind of diagram, which I will be calling as temperature entropy diagram. So earlier, while I have plotted the diagram, you have seen me plotting pressure, temperature, specific volume, pressure, specific volume diagrams only. Okay, so today I am plotting the diagram in between temperature and entropy. So while we plot the temperature entropy diagram for our water as a pure substance, we will be finding that our liquid vapor dome will be something like this. Okay, so this will be our liquid vapor dome. Here we will be having critical point, and in this region we will be having nothing but subcooled state. Here we will be having liquid plus vapor, and here we will be having superheated state. Okay, so now on this particular diagram, if I have to plot the constant pressure line, so constant pressure line looks something like this. So these are nothing but my constant pressure lines on the TS diagram. So say this is pressure P1, this is pressure P2, which is greater than P1. Okay. Then if I have to plot constant specific volume line on this diagram, so constant specific volume line will be looking something like this on. So this diagram, this line is nothing but constant specific volume line on my TS diagram. Okay. So I have just only introduced you that like PT, PV and TV diagram, we can also plot one of the very important diagram which we call as nothing but our temperature entropy diagram. Okay, and this is how different parameters appears or looks on, for example, constant pressure line, constant specific volume line. So this is how these looks on this temperature entropy diagram. Okay, so at the moment I will not go into very much details of this particular, because already while discussing the steam tables, I have explained you how to obtain the value of entropy from our steam table. Okay, one very important point, like I have told you earlier, that for the case of enthalpy or specific volume, we have a value of enthalpy within the two-phase region equal to HF plus X times of HFG. So similarly for entropy also, we have S is equal to SF plus X times of SFG. Okay, so this formulation is applicable for the entropy also while our substance is in the liquid vapor dome. Okay, now one of the, if you once again recall my earlier lecture, I have told you that we are having one very important diagram which we call as nothing but Mollier diagram. Okay, so Mollier diagram is nothing but a curve in between the enthalpy and entropy. Okay, so diagram in between the specific enthalpy and the specific entropy is particularly referred to as Mollier diagram. It is one of the very famous diagram, because whatever the steam tables we are having, all the steam table data can be obtained from this single HS diagram. Okay, so on this HS diagram, if I plot the liquid vapor dome, it looks something like this. So somewhere over here we are having our critical point. Okay, and if I plot the constant pressure lines on this diagram, so constant pressure lines looks something like this. So say this is some pressure P3 which is greater than P2, then some one more pressure, say this is my pressure P2 which is greater than P1, and say this is some another pressure P1. Okay, so what we can do while solving the numerical problems, rather than going into the steam tables, one can directly use this particular Mollier diagram for representing the thermodynamic state of the substance, because on this diagram we plot each type of line: constant pressure, constant temperature, constant specific volume, and generally we try to locate our thermodynamic state, and from after locating the thermodynamic state we can obtain all other properties from a single diagram. Okay, so this is one very important diagram which you can use for obtaining the property, and it is referred to as Mollier diagram. Okay, now let me define
Sir,
one.
red line. Then what? The red line. What is representing by red line in the Mollier diagram?
Red line is actually your liquid vapor dome. So this is your critical point. Okay, so this is your critical point, and the line on the right hand side is saturation vapor line, and on the left hand side of the critical point is nothing but saturation liquid point. So this is saturation liquid line. Okay, so in between this dome we will be having our dryness fraction varying from 0 to 1. Okay. Okay, now let us see the entropy change for reversible processes. Okay, so already I have defined that for reversible process ds will be nothing but equal to integral del q by t. So now let us try to see this formulation with the help of some example. Okay, so as an example, what I am doing, I am considering, say my nothing but what I am considering my reversible adiabatic cycle. So Carnot, reversible Carnot cycle. Okay, so let me plot the reversible Carnot cycle on temperature entropy diagram. Okay, so the very first process of our reversible Carnot cycle is nothing but isothermal heat addition. So in case of isothermal heat addition, temperature will remain constant, and if I consider that our working medium is in the two-phase regime, then we will be operating our Carnot cycle in between saturated liquid and saturated vapor curve. Okay, so I'll be having this process number 1 to 2, and it is constant temperature heat addition. So we are adding QH amount of heat, and let us consider the temperature of this point nothing but equal to TH. Okay, then if you try to see the process number 2 to 3 is our reversible adiabatic process. Okay, so process number 2 to 3 is reversible adiabatic process. Now we know that for a reversible process ds is equal to integral del q by t. Okay, so if our process is reversible and at the same point of time it is adiabatic, so now what will be happening, our dq value will be equal to 0, and finally we will be finding that ds is equal to 0. So if ds is 0, s will remain constant during that particular process. So it means that our process will be nothing but isentropic. Okay, so this is one very important point, that if our process is reversible, then I can say ds is equal to integral del q by t, and if it is adiabatic, then dq will be equal to 0. So in that case my ds will be becoming equal to 0, and this means that our entropy is remaining constant during that process. So because of that I can call this process to be isentropic. Okay, so one very important point I have now explained, that If we have a process which is reversible and adiabatic, that process will be nothing but our isentropic process. Okay, so for a reversible adiabatic process, entropy will be constant. However, the reverse of this statement will not be always true. Why? That we will see in the subsequent lectures. Okay, but this statement is always true, that if we are having a reversible adiabatic process, that will be always the isentropic process. Okay, so it means during process number 2 to 3, now my entropy will remain constant. So I can represent constant entropy line over here. So constant entropy line will be nothing but a vertical line. So this is my point number 3. Then we have reversible heat rejection process. So in the heat rejection process, I will be removing some QL amount of heat from 3 to 4, and obviously this heat rejection we are doing at temperature TL. Okay, and once again, then 4 to 1 we are having nothing but reversible adiabatic compression process. So reversible adiabatic means isentropic. So we have isentropic compression. Okay, from process number 4 to process number 1. Now, if I have to calculate the entropy change for the different individual processes, so you can clearly see that entropy change for process number 1 to 2, if I take process number 1 to 2, so we know that entropy change for process number 1 to 2 ds, which I can simply say S2 minus S1 will be nothing but equal to integration from 1 to 2 del Q by T. Okay, and over here del Q is nothing but QH amount of heat we are adding, and we are adding this heat at constant temperature TH. Okay, so because our Q amount and T amount, they are actually constant, they are not varying. So because of that, this integral 1 to 2 del Q by T will be nothing but equal to QH divided by TH. Okay, so from here I am able to get that my QH is nothing but equal to TH times S2 minus S1. Okay, so what is this? This is nothing but equal to area under this particular diagram. Okay, so let me show it once again. So for process number 1 to 2, I have got that my QH is nothing but equal to TH times S2 minus S1. Okay, and if I show my property diagram, so this is my TS diagram, and this is liquid vapor dome, and this is our process number 1 to 2. Okay, which is having temperature TH, and we are adding QH amount of heat over here. Okay, so what we will be finding ultimately we will be finding, if this is my S1 and this is my S2, we are having this area under this TS diagram as nothing but the amount of heat which we have added during the process number 1 to 2. Okay, now if you see process number 2 to 3, during process number 2 to 3, our entropy is actually constant. So you will be finding that for this process S2 is equal to S3. Similarly, for process number 4 to 1, S4 is equal to S1, because these are nothing but isentropic process. Okay, now let us go to process number 3 to 4. So if I go to process number 3 to 4, in case of 3 to 4, I can write that S4 minus S3. Okay, so S4 minus S3 will be equal to integral del Q by T from 3 to 4. Now you can see clearly in this diagram, our temperature is equal to TL when process 3 to 4 is happening, and during this process our working fluid is actually rejecting some QL amount of heat. Okay, so as it is rejecting some amount of heat, so because of that my S4 minus S3 will be equal to nothing but minus QL divided by TL. So from here we will be finally finding that QL is equal to TL times S3 minus S4. Okay, so if I once again represent this process on my TS diagram, so this is my liquid vapor dome, and say this is our process number 3 to 4. Okay, so I will be finding that during this process 3 to 4, this is my temperature TL. So this area, whatever I am having under the TS diagram, that is actually our amount of heat what we have rejected. Okay, so this is the QL amount of heat which has been rejected during this reversible isothermal process. Okay, now we know from our first law of thermodynamics that work is equal to nothing but QH minus QL. Okay, so that is the net amount of work done, whatever we will be getting from our reversible Carnot cycle. Okay, so as per this formulation, if I have to plot, once again I have to show it on the TS diagram. So let me first plot my cycle. So this is 1, 2, 3, 4 and 1. So we have seen that our entire area represents the amount of heat added, and area from 3 to 4, below that it represents the actually amount of heat what we have actually rejected. So obviously QH minus QL will be nothing but this area over here, whatever we have, the area enclosed within this cycle. So area enclosed within the cycle represents actually QH minus QL. So that's why it will be equal to net amount of work done, whatever we are obtaining from our thermodynamic reversible Carnot cycle. Okay. Now let me define some thermodynamic property relations.
Sir,
Yes.
sir, is it necessary that for every reversible cycle S2 will be equal to S3, or is it just a special condition that we have taken?
It will not be always reverse for reversible cycle. It will be true for reversible adiabatic process. Okay. So this is the very important point which you have to take care, that if our process is reversible, I can write ds equal to del q by T. Okay, and if process is adiabatic, then my del Q will be equal to 0. So then only our ds will be 0 and s will be constant. So it means for a process, if it is reversible and adiabatic, then only I can write that S is remaining constant. Is this point clear?
Yes, sir.
Okay, so now let me take up the thermodynamic property relations. So we know from our first law of thermodynamics, if I write first law of thermodynamics for closed system, we know that del Q minus del W is nothing but equal to, if I consider that in case of my closed system, kinetic energy and potential energy are negligible. So I can simply write del Q minus del W as nothing but equal to du. Okay. If I write this equation on the per unit mass basis, so I'll be finding del small q minus del small w equal to d into u. So this is nothing but on per unit mass basis. Okay. So this equation is our first law of thermodynamics for the closed system, control mass system. Okay. Now just now, because while we are writing this particular equation for first law of thermodynamics, every time we try to consider that our process is nothing but quasi-static. So quasi-static is an ideal reversible process. So that's why for this ideal reversible process, I can write del Q as nothing but equal to T times ds. So just now we have seen that our del Q is nothing but equal to T into ds. So that is, I have shown you in the previous slide. Okay. And for work done, we already know that in a closed system, we are having actually displacement work. So we define displacement work as P times D into V. Okay. And this will be equal to du. Okay. So now, apart from this, one more thing I can do. If I say that my substance which I am considering, if that substance is nothing but an ideal gas. So if our substance is an ideal gas, in that case, I can even write that my TDS is equal to, let me first write TDS is equal to nothing but du plus PdV. So that is my generalized form which is applicable for any kind of fluid medium. And if I now take the assumption of ideal gas, then I'll be getting one more simplified thing, that TdS is equal to, in place of du, I can write Cv naught into dt plus P times dV. Okay. So this particular equation, whatever I have got, now you can see the distinction over here. This equation is actually mainly derived from this particular equation, which represents del Q minus del W equal to du, where du is the only property of the system, whereas del W and del Q are the path functions. Okay. However, if we consider that we are applying this particular formulation for a reversible process, I can write del Q as equal to TdS and del W as equal to PdV. So finally, I'll be finding my equation as TdS equal to du plus PdV. Okay. So what is the important characteristic of this equation? If you try to see, this equation involves only thermodynamic properties. Okay. So one of the important characteristic of this equation is it is involving only the thermodynamic properties. So it is representing the relationship between different thermodynamic properties what we have. Okay. So as it is representing the relation only in between the thermodynamic properties, so we know that our thermodynamic properties are nothing but state functions. Okay. So thermodynamic properties are nothing but our state function. So it means that this particular equation is applicable for any kind of process. By meaning of any kind means whether process is reversible or irreversible. Okay, so this is one very, very important point which I am highlighting over here. Though while we have derived this property relation, we have considered that we are using the formulation of reversible process. Okay, but finally this equation has become a form, or this equation has taken the form which takes which consists of only the thermodynamic properties, and we know that thermodynamic properties are nothing but our state functions. So that's why I can say that this equation will be applicable for any kind of process. Okay. However, if I have to integrate this equation, integration has to be done only along the reversible path. Okay, because this replacement of del Q, we know that this replacement of del Q by T into ds, it is actually applicable only for reversible path. Okay, so this is applicable only for reversible path. That's why if I have to integrate, integration has to be done. Integration has to be done along reversible path. But in general, if I am only applying this particular equation, so I can apply this equation for my any process, whether it is reversible or irreversible, because it is involving all the properties, and the properties which we are having, these are nothing but our state functions. Okay, so that's why this equation can be applied for any process irrespective of its type. However, if we are using this particular equation and then from this equation actually we are trying to integrate this particular equation for path, so it has to be only integrated along a reversible path, because this assumption we are taking del Q equal to TdS, that is only applicable for a reversible path. Okay, so this equation is known as first thermodynamic property relation. And if I take one more equation, so we know our H is nothing but equal to U plus PV. Okay, so if I take DH, DH will be equal to du plus PdV plus V times dP. Okay, so now we know from our first law of thermodynamics for closed system, from that actually we have got one property relation which tells that TdS equal to du plus PdV. So finally I can say that my DH is nothing but equal to T into ds plus V into dP. Okay, so from here finally I can say that my TdS is equal to D into H minus V into dP. So this is my another second very important property relation. So this is also one property relation, and both these property relations, whatever I have derived, these are known as Gibbs property relations. So these are also known as Gibbs first two property relations. Okay, so Gibbs have total given 4 property relations. So these two are also called as Gibbs first two property relations. Okay, now one very important characteristic of this particular equation I would like to highlight. So from this particular equation, actually if you see the origin of this equation, it is coming from enthalpy, and enthalpy is something physically, if we see, enthalpy is actually associated physically associated with the flowing stream, because it includes the inherent energy content, internal energy, plus the amount of flow energy which is associated with the system. Okay, so it means fundamentally, if we try to observe, this particular equation is actually derived on the basis of considering the idea of flowing stream. And flowing stream mainly comes into picture when we have our open systems, because in open system only we allow the entry and exit of the mass streams from our boundary of the control volume. Okay, so now you can see, if you take the analogous form to our law of conservation of energy, this TdS term is nothing but representing our heat transfer, net amount of heat transfer for a process, and this dH is nothing but representing the change in energy content. So obviously what third quantity is missing? So the third quantity missing is our work interaction. So it means this VdP over here should represent nothing but our work interaction associated. Okay, so that's why what we do, we call this VdP as delta W as minus VdP, where this delta W is nothing but work done by the open system. Okay, so we know in case of closed system, we have seen only one specific kind of work which we call as displacement work, and that work is also known as PDV work. However, if we consider our open system, in case of open system, I may represent work by minus VdP, and finally I can say that my W amount of work will be nothing but equal to minus integral of small v into dP. So this is our work done in an open system. Okay, so this is work done in an open system. So if I give you an example, what will be happening if I take the process of pump? Okay, so we have seen in our temperature entropy diagram that if I take the process of pump, say my 4 to 1 is nothing but process happening inside the pump. So for this particular process, what will be happening? Our entropy will be constant. So entropy means ds is nothing but equal to 0. So for this process 4 to 1, our ds term is equal to 0, because S1 is equal to S4. So now what will be happening? I will be finding that my H1 minus H4 will be equal to, if you see this property relation, so H1 minus H4 will be equal to integral of VdP. So integral of V means specific volume, integral of specific volume from, so this integral I have to do from 1 to 4 to 1, and this integral of VdP I have to take. Okay, so now you know that in the reversible this process, what we are doing, we are nothing but adding certain amount of pump work. Okay, so and this pump work, if you apply the steady flow energy equation from our earlier knowledge, you will be finding that this pump work per unit mass will be nothing but equal to H1 minus H4. Okay, so this will be coming from our steady flow energy equation. So SFEE, if I apply the steady flow energy equation, I'll be finding that pump work per unit mass is nothing but equal to H1 minus H4. So this H1 minus H4 is now becoming equal to integral of VdP from our property relation while we are deriving this second property relation. So it means I can say that my integral of VdP is nothing but equal to work done in an open system. Okay, so this is one very, very important point which we have got from this property relation. From our steady flow energy equation, we are getting pump work per unit mass equal to H1 minus H4, and H1 minus H4 is becoming integral of VdP. So that's why I can say that this integral of VdP is nothing but work done in an open system. Okay, so this point now you should remember how to calculate the work done in an open system.